Okay, so this is the midterm review for EGME 417 in spring 2023. Okay, so we have our first midterm coming up this week, and so what I'd like to do in this review is just review all of the kind of important concepts that I need you to know. Right. Remember, this midterm is going to be based on basically just the concepts and the theory only, and so you're not going to do any math. Okay, and so I think. It's a little bit hard to kind of do this while you're in the semester, but hopefully what you see from this review is that it's, a lot of the same idea that we've kind of been applying over and over again. And then we've basically just been applying it to different problems. Okay. So kind of the central thing that's kind of holding everything together in this first section of the course is this idea of a finite difference approximation of a derivative. Okay. Okay. And so a finite difference approximation of a derivative is this idea that, you can take a derivative, which is a calculus-based quantity, and then replace it with an algebraic expression. Okay. There's lots of different types of finite difference approximations, depending on what kind of situation that you're in. But, here's kind of the basics of it. And so if you have a derivative, okay, so we have just a basic first order derivative here. We can replace this with, an algebraic expression. So basically a difference over a distance. Okay. Okay. And so what I've done there is I've replaced it with an algebraic expression. Okay. And so the next question you may ask, or you may be wondering is, what exactly are these things here? Okay. And so usually when we apply finite differences, we're usually doing it on some kind of, I call it a grid, but it's basically just a bunch of nodes that are together, where each node has this particular quantity. Okay. Okay. So here I have a grid. This one is 7 nodes. Okay. And each node has a particular value of u, where u here is our function of interest. Okay. Good. And so to take the derivative, let's say that we want to take the derivative around node 4. Okay. And so here I would equal to 4. Okay. And so in that situation, we would take basically the value of u at I plus 1, which is its right neighbor, minus the value of u at I minus 1, which is its left neighbor, and then divided by delta x. Okay. And so we'd have u 5 minus u3 divided by 2 delta x. Okay. Remember, delta x is the spacing in between the grid points right here. Okay. So that's the idea. It's basically just the application of rise over run, but in kind of a novel way. Okay. And the most important thing that it gets us is that we take an expression here, which essentially is a calculus expression. Okay. And so I'm sure everyone's kind of familiar with calculus at this point. And so the thing with calculus is that you have to solve the problems, calculus problems, differential equation type problems in a very particular way. Okay. And in fact, those methods actually are, if you look at them, are very limited in that you can't solve a lot of very complicated calculus problems, with hand calculations. Okay. But by applying this finite differences, you change the problem instead to an algebra problem. Okay. And that's really key because when you use computers to solve problems like we do, algebra is kind of the way to go because that's what's going to be the easiest to solve on a computer. Okay. And so how do we apply this? And so that's the basic idea with the finite differences. Basically, we want to apply this to solve differential equations. because differential equations are among kind of the hardest, the most difficult engineering problems to solve, and they show up very commonly in kind of no matter what kind of field that you're looking at. Okay. And so if you're in any kind of analysis role, whether you're a structural engineer, fluids engineer, thermal engineer, you're going to be solving differential equations. Okay. And so the idea is that you're going to take your differential equation and you're going to replace all of the derivatives with a finite difference approximation, and then you're going to solve that equation on a grid. Okay. Okay. And so let's come back to an example that we did in class before. Okay. And so this is a simple 1D diffusion equation. So this is something that's very pretty straightforward. Okay. And so we'll just pull it up here. Okay. Okay. So you have d squared phi dx squared is equal to 6x, right? So this is a differential equation. And so this is basically, we have a derivative of the function phi, and we have an equation that relates to its functional properties. And we want to solve this equation for phi. Okay. So normally what we want to do is we want to solve this equation. You want to solve this equation to obtain a function phi of x. Okay. And that will be our solution. So basically, remember that the solution to a differential equation is a function that satisfies the original equation. Okay. And so a function phi of x that satisfies this derivative equation would be the solution. Okay. Of course, when you're talking about differential equations, you're not talking about just the equation itself, but you have to have boundary conditions as well. Okay. And so, for instance, we'd have phi of 0 is equal to 1, and then d phi dx at x is equal to 1 is equal to 0. Okay. All right. So this is a pretty simple problem, but I want to kind of walk you through this process in terms of what I can expect you to do on the exam. Okay. So just like we discussed in class, I'm not going to ask you to fully solve these problems with finite differences, because that involves solving a very large linear system. Okay. And so all I really want you to do in these problems is to take this equation, take the boundary conditions, and set up the linear system that you would use to solve it. Okay. And so your output or the final answer in these types of problems is going to be a matrix form of the algebraic equations. Okay. Okay. And so with that, usually what I'm going to do as well is I'm going to give you some kind of grid to solve the solution on. Okay. And so in this case, let's say that we have a 5-node grid. Okay. And so what I want you to do is I want you to set up, for this 5-node grid, and we can assume a value of delta x. So let's assume delta x is equal to 0.25. Okay. And so for this grid and this grid spacing and this differential equation, I want you to set up the finite difference algebraic system. Okay. All right. So first thing off the bat that you should realize is that the number of equations that you should get should equal the number of nodes that you have in your system. Okay, so we have 5 nodes here, and so that means we're going to need 1 equation per node. Okay. Okay. Right. So in this particular problem, we're going to need 5 equations. Okay. And so I emphasize that because every problem I'm going to give you is probably going to have a different number of nodes. And a lot of times I see people are and this usually happens when people just write down examples on their cheat sheet. They say I may give you a problem with 7 nodes, and then you may write. I've seen people write this exact thing where we need 1 equation per node, and they still write 5 equations because they're just kind of copying right off the example. Okay, so count the nodes, and that's going to give you the number of equations. Okay. Okay, so from here you can kind of approach this in different ways, and so just like we've discussed in class, there's kind of 2 different kind of sources or 2 different types of equations that you're going to need. Okay, and so on the one hand, you're going to need the finite difference approximation of the main equation. Okay. Okay, and so this is going to be applied to all the interior nodes. Okay, and then you also have your boundary condition equations. Okay, and these will be applied to all your boundary nodes. Okay. All right, so you can start with either one. I mean, you're going to need all of it eventually, and they're kind of separated from each other, so you can kind of work in parallel. Okay. Usually, what I like to start with is this one. Okay. And so let's do that one first. Okay. And so to get the interior nodes equations, you need to start with the original equation and replace all the derivatives with finite differences. Okay. So let's go back to the original equation. Okay. In this case, we only have 1 derivative. And so let's go ahead and replace that derivative. Okay. Okay. All right. So that is that's our finite difference approximation. Okay. And from here, technically, you can just start plugging in and getting equations. But what I like to do is simplify this a little bit, just to make the solution a little bit more, easier to read. Okay. All right. So let's multiply both sides of this equation by delta x squared. Okay. Just so we can get away from that denominator. So usually denominator quantities are, a little bit not as pretty. Okay. But you don't have to do this. And so, on the exam, if you want to just plug straight into this, that would be fine. Okay. I'm not going to ding you on any kind of algebra, things like that, if you prefer it in a different form, as long as you're consistent. And, and so if you divide by delta x squared here, and you leave that on the left-hand side, make sure you kind of stick with it and don't have a delta x squared suddenly appear on the right. Okay. And so there's flexibility. And so, there's more than one there's more than one answer for these problems. As long as you're consistent with the algebra. Okay, but this is kind of how I like to do it. But you can do it however you like. Okay. Okay. So that's there. That right there is the generic equation that we can apply for all the interior nodes. So now let's actually apply it. Okay. And so if we go back up to our grid right here, we can see that we have 3 interior nodes, right? And so we have node 2, node 3, and node 4. Okay. So remember, interior nodes are ones that are not sitting on the edges of the domain, okay? And so in 1D, we have a left edge of the domain and a right edge of the domain. And so that's going to be node 1 and node 5 in this case, okay? And so we're going to apply this interior node equation to three instances, okay? Okay. So let's go ahead and do that. Okay. And so if we apply this at I is equal to 2, so that's node 2, then we have phi3 minus 2 phi2 plus phi1 is equal to 6xi, okay? Remember, xi here, xi is the physical coordinate of the node in question. Okay? Because if you go back up to the grid right here, each node there is going to have a physical location based on the grid spacing, okay? And so we know, so here's a couple things we know. And so on the left-hand side, we know that we start at x is equal to 0, okay? And we know the space in between each node is delta x, which in this case is 0.25, okay? And that's the same between all the nodes, okay? Right, and so if we kind of label this, we know that x1, the x coordinate for node 1, there's going to be 0. x2 is going to be 0.25. x3 is going to be 0.5. x4 is going to be 0.75. And x5 here is going to be 1.0. Okay. And that was just based solely on, the grid spacing, which was given to you in this problem, okay? And so make sure you use that grid spacing is very important, okay? And so with that in mind, we know that from the table above, or from the figure above, x2 is equal to 0.25, okay? And so the right-hand side of this equation is going to be 6 times xi, which is 0.25, multiplied by delta x squared, where delta x is just our grid spacing. So this is going to be 0.25 squared. Okay. I don't have my calculator on me, and so normally you would punch that into a calculator and get a decimal from that, but that's the basic idea. Okay, so let's go ahead and apply this to nodes 3 and 4. Okay, so you apply it to node 3. I plus 1 from 3 is 4. Okay, then we come to the right-hand side. And so we have 6 times xi. We know that x3 here is 0.5. Okay, and then we're going to multiply it by delta x squared, which is 0.25 squared. Okay, and then finally we apply for x4. Okay, and then that's what we obtain. Okay, all right, and so that's 3 equations. So that's 3 out of 5 equations down. Now let's work on the boundary conditions. Okay, all right. All right, so the boundary conditions are basically the equations that we need to solve in order to get the values of the solution at the boundaries. Okay, and so the reason we do this is that if you look at our finite difference equation here, okay, the finite difference equation, like most finite difference equations, relies on the fact that you have neighboring nodes. Okay, and so you need an I plus 1 node and I minus 1 node. Okay. If you look at our grid, if you look at nodes 1 and 5, those are our boundary nodes. They may have a neighbor on one side of them, but they don't have a neighbor on the other side, right? And so if you look at I is equal to 1, node 1 here does not have a neighbor on its left, okay? And so we're not able to apply our finite difference approximation on that particular node. Okay. And so what we need to do instead is apply these boundary conditions on that space. Okay. All right. So let's start with the left boundary condition. And so the left boundary condition in this case is applied at x is equal to 0. Okay. And from the problem, we can see that phi of 0 is equal to 1. Okay. All right. Okay. All right. Phi of 0 is equal to 1. And so what this is saying is that this equation is basically saying that when x is equal to 0, then phi takes on a value of 1. And so in other words, we're directly specifying the value of our solution at the left boundary. Okay. All right, so let's formulate this into an algebraic equation that we can use together with our other equations. Okay. All right, so let's break the statement down. And so, the first step is to look at the fact that we're directly specifying the value of the solution. Okay. And so at x is equal to 0, the value of the solution at x equal to 0 is phi 1. Okay. Okay. Right, because we have, in this case, we have a node that's sitting right on the boundary. Okay. And so that node is going to be the value of phi at that node is going to be our solution. Okay. Okay. And in this case, what we're setting it to is equal to 1. Okay. And so we're going to have phi 1 is equal to 1. Right. Okay. And so node 1. Okay, so node 1, like we said, node 1 is sitting right on the left boundary, and so the value of the solution at that node is phi 1. Okay, and we're directly setting its value equal to 1. Okay, and so that's it. That's our equation. Right? So this is our I is equal to 1 equation. Okay, so I is equal to 1 equation is going to be phi 1 is equal to 1. Okay, okay, and so that's the left boundary condition. Okay. If you were curious, this type of boundary condition, we give it a special name. So this is called a Dirichlet boundary condition. Okay. All right. All right. On the right boundary, if you go back up to our problem, okay, we have this boundary condition where d phi dx at x is equal to 1 is equal to 0. Okay. In other words, what we're saying is that the value of the derivative at x is equal to 1, or in other words, the value of the derivative on the right boundary is equal to 0. Okay. And so in these situations, whenever you have a boundary condition on a derivative, we know that that's called a Neumann boundary condition. Okay, and so in these situations, let's take our equation for the derivative for the boundary condition. Okay, and just like we did for the interior nodes, we're going to take this equation and replace the derivative with a finite difference. Okay. Okay. Right, but we have to be careful here because remember we're on a boundary, right? And so because we're sitting on a boundary, we have to be careful about how we set this derivative so that we can have all the neighboring nodes that we need. Okay. Okay. So let's go ahead and replace this with a finite difference. Okay. Keeping in mind that since we're on the right boundary, we have no right neighbor. Okay. Okay. And so let's go ahead and plug that in. And so, we have a first order derivative here, so that helps us a lot. Okay. And so if we look back at kind of our repertoire or our arsenal of first order finite difference approximations, we know that we have one that only uses a left neighbor, which is backward difference. Okay. All right. And so backward difference we phi minus phi minus 1 divided by delta x. Okay. Right. And so we replace this derivative here with this finite difference. Okay. And we set that equal to 0. Okay. Because the boundary condition says that this should be equal to 0. All right. And so this should work because, we have phi sub I. So phi sub I is going to be that exact boundary node, which is node 5. Okay. And we have phi minus 1, which is going to be its left neighbor, okay, which exists because we're on the right boundary. Okay. Okay, so let's go ahead and simplify this equation a little bit. So let's go ahead and multiply both sides by delta x. Okay, so that's going to have a cancel. And so we have phi minus 1 is equal to 0, right? Let's apply this at I is equal to 5 because that's where our boundary condition is. Okay. And so in the end, we get phi 5 minus phi 4 is equal to 0. Okay. All right, and so that's about it. And so, now that we have applied our boundary conditions, we have an equation for I is equal to 1 and I is equal to 5. Okay. Once we combine that together with our interior node equations, I is equal to 2, 3, and 4, then we have everything that we need. Okay, so all we have to do here is kind of put it all together into matrix form. Okay. All right, so let's go ahead and do that. So I'm going to write down all the equations, but I'm going to reorder the terms a little bit just so it's a little bit easier to see how the coefficients kind of match up into the matrix form. Okay. All right. So let's start with I is equal to 1. Okay. So I is equal to 1. Remember, our equation was phi 1 is equal to 1. Right. All right, let me do this as well, just so that you can see. Okay, it's not going to change the equation, but it's just going to show you, where the coefficients are. Okay. Okay. And so phi 1 is equal to 1 is the exact same thing as phi 1 plus 0 times phi 2 plus 0 times phi 3 plus 0 times phi 4 plus 0 times phi 5 is equal to 1. Okay. Okay. I'm putting those there so that you know kind of where those coefficients come from. Okay. All right. So let's do that. I is equal to 2 equation. Okay. So let's come back up here. So I is equal to 2 equation is this one right here. Okay. All right, so I'm going to switch the phi 1 and phi 3 just so that you can kind of see. Okay, so once again, I added zeros there for the terms that aren't present in the equation, okay? And this is equal to 6 times 0.25 times 0.25 squared, okay? All right, so let's go ahead and continue that pattern for all the other equations. Okay, so that's all our interior nodes. And so finally, we have our boundary condition. Okay. All right. So I've written down our 5 equations here, and I've included all of the coefficients for all the terms that even aren't in the equations. Okay. And so now to put it in matrix form, we basically just extract the coefficients in front of the phi terms. Okay. All right. And so for row 1, we have a 1, okay, in front of phi 1, and then we have zeros everywhere else. Okay. We have 1 minus 2, 1, 0, 0. Then we have 0, 1 minus 2, 1, 0. Then we have 0, 0, 1 minus 2, 1. Okay. And we have 0, 0, 0, minus 1, 1. Okay. All right. And so all this is multiplied by phi 1, phi 2, phi 3, phi 4, phi 5. And this is equal to the right-hand side. So we have 1, 6 times 0.25 times 0.25 squared, 6 times 0.5 times 0.25 squared, 6 times 0.75 times 0.25 squared, and then 0. Okay. All right. And so this is the final solution. Okay. So this is what I would want you to do on the exam. Okay. So you would stop here. And so I would, of course, I would give you partial credit for everything up to this point. But this is the final deliverable. So you don't need to solve this. So you don't need to solve this linear system. But this is what I would expect. Okay. All right. And so, like I mentioned in class, with computational heat transfer, we're doing a lot more than just typing code, although, the code is a big part of the class. There's still also a pretty significant component of the theory that we need to go over as well. Okay. And so the theory in this class is, how do you take a complicated differential equation, turn it into an algebra problem? Okay. So that's what I'm testing you on the exam. And then the other component of this class is, how do you take that algebra problem and solve it in code in a way that's kind of flexible and adaptable. Okay. And so that coding part, that second portion, I'm not going to be testing you on this exam, but that's going to come up in the final project. Okay. Okay. All right. And so that's kind of a summary of kind of the 1D problems. Okay. Let me just kind of double check everything just to make sure I got it all. Okay. Okay. All right. So, I have about 20 minutes remaining, a little bit over 20 minutes. And so let's review a little bit about 2D problems. Okay. And so, I spent a lot of this review on this kind of very simple 1D problem because, when you go up to 2D, the only, I would say kind of the more difficult thing is kind of the mental block of like, oh my gosh, we're in 2D, it's going to be a lot more complicated. Okay. But, we went through this entire process right here just for me to show you that, it's this same process, right? And so we're going to take our differential equation, we're going to replace its derivatives with finite differences, and then from there we get algebra problems that we just simply kind of plug in, okay? And so, what I want you to take away from this section, what I want you to take away and what I want you to really know for the exam is not really, just kind of the plugging and chugging into the equations that we have in class. I really want you to nail down this process, okay? Okay. And so I don't want you to just, I know it's very tempting because, just kind of based on how the lectures have gone, we've gone through this process in the lecture. We've gone through it many, many times. But a lot of times we arrive at an equation where it looks like you can just kind of plug in and solve for it, right? But I don't want you to do that. And so, for the exam, I want you to go through this whole process of, you take your differential equation, you replace it with a finite difference approximation, okay? And then, and then you kind of plug in from there, okay? Same thing with the boundary conditions. And so, I really want you to learn this process because, finite difference, in the kind of the grand scheme of things is really just one method, okay? It's a nice method, especially to learn about the kind of this idea. But, what I really want you to take away from this class is not just, a particular method and just plugging into that particular method or coding that particular method, okay? I want you guys to get into this mindset of, computational, how do you set up a computational problem, okay? And I realize, it is hard. It's very different from kind of maybe how you've approached a lot of other problems that you've had in other classes. But because this is kind of your, for a lot of you, basically your only exposure to any kind of computational class, I think it's really important to kind of, get that kind of basic mindset down, get that basic concept down, so that if you do want to pursue this further, you're kind of well equipped to do that. Okay. Oops. No, that was weird. Okay. Okay. And so right now, I'm kind of forcing it. I'm kind of mandating that you have to follow this process, right? But I'm not doing that just because, right? So I'm doing it so that you really kind of learn and you can kind of demonstrate to me that you really understand this kind of, not only just, the finite difference method, and you can kind of plug in and solve a problem with that. You really kind of understand what's going on in the method, why we're doing each step, and so that you can apply that to the future, okay? Okay, and so with that said, let's go ahead and move on to a 2D problem. And so just because of the time, limited time that we have remaining, let's do a 2D convection problem, okay? And as a bonus, if you've made it this far in the video, let's do the homework. Let's do the homework problem, okay? And so this is problem 2B on homework 3, okay? So what we have is 2 partial squared phi partial x squared plus partial squared phi partial y squared is equal to 3 partial phi partial x plus 80x partial phi partial y, okay, plus cosine of pi y. Okay, and then I asked you to solve it on the following grid. Okay, for the boundary conditions, we have phi is equal to 50 on top, phi is equal to 75 on the left, partial phi partial n is equal to 0 on the right. and we have partial phi, partial n, it's equal to 20 on the bottom. Okay. Okay, so we have a 2D problem here. Of course, it has convection because we have our first order derivative. Okay. And so for 2D problems, even for a very modest grid, this is a 4x4 grid. This is about as modest as you can get. Even so, writing 16 equations is pretty extreme. Okay. And so in these types of problems, I'm not going to ask you to write down all 16 equations and make a 16 by 16 matrix. Okay. What I'm going to do instead is, just have you write down specific equations. Okay. But our process is going to be the same. And so, just like we did with the 1D problem, first thing we can do is we can make our interior node equation based on the original equation here. Okay. And then we can write down specific specific boundary condition equation based on the different boundary conditions. Okay. Okay, so let's start with the interior node equation first. Okay, so exact same process that we did before. So we're going to take our differential equation here and replace each derivative with the finite difference. Okay. Okay. And so first we have partial squared phi partial x squared. Okay, so we're going to replace that with a second order finite difference. Okay, so you have phi I plus 1 comma j minus 2 phi I comma j plus phi I minus 1 comma j. Okay, plus delta x squared. Then we have a second order derivative in y. So that is the, that's all the diffusion terms, okay, the second order derivatives. Next, we have the convection term, since we have 3, okay. And so, of course, with convection, remember, you have a choice. And so, remember, you can, you can either discretize the convection derivatives with either central difference or an upwinding scheme, okay. All right. And so, for the homeworks, I think I asked you to specifically use an upwinding scheme, okay? But for the exam, I'll actually give you a choice. And so if you, if you can choose central difference, okay? The only condition that I have is that your scheme be stable, okay? Okay. And so if you're using an upwinding scheme, then you're guaranteed stability, okay? But remember, you have to upwind in the correct direction, okay? If you use a central difference scheme, you have to show me, based on the parameters of the problem, that your scheme is going to be stable, okay? And remember, the way that we do that is we check the Peckley number, okay? And so the Peckley number is u times delta x divided by k, which is the diffusion constant, okay? And so in order for it to be stable, this has to be less than 2. Okay. All right. So generally speaking, if you have a convection term and the velocity is fairly low, okay, and so in this case we have a velocity of 3, that's usually safe to use the central difference scheme for, just because the velocity is low, and so likely the Peckley number is going to be less than 2. Okay. And so that's exactly what I'm going to do. And so for this 3 here, I'm going to, or for this x derivative, I'm going to replace it with a central difference. Okay. Okay. All right, and then we have the y derivative. And so the y derivative has a coefficient of ADX. Okay. Of course, this is a variable y velocity, and so that's going to change as a function of x. Okay, so that's what the x is there for. Okay, so let me drop in x sub I. Okay. But because this velocity here, it has a much higher magnitude, so it has an 80 in front. Granted, it's also multiplied by x, and the grid spacing here is 0.25 or 0.5, excuse me. Okay. And so, what I'm going to say is that this velocity is going to have a higher magnitude. So let's use an upwinding scheme for this, okay? And so for a positive y velocity goes basically from down to up, okay? And so the upwinding side is on the bottom, okay? Okay. And so this is for a positive y velocity. Okay, and so with that said, an upwinding scheme in the that goes from the bottom up. Okay, the scheme for that is going to be phi I comma j minus phi I comma j minus 1. Okay, all divided by delta y. Okay. All right, so we use j minus 1 because the upwinding side is the bottom, and so we need to utilize the bottom neighbor. Okay, and then we plug in 4 for that. All right, and then the last thing is going to be our source term. And so our source term here is cosine pi y. Okay. And so that is that. Okay. Okay. All right. And so from here, we can simplify this equation. Okay. And so there's quite a bit of algebra to do. But let's go ahead and do that. Okay. All right. So for now, let's go ahead and assume delta x is equal to delta y is equal to delta. Okay. I'm going to do everything in symbols just because of the time remaining. But just know that when you're doing this on the exam, you can go ahead and plug in for this. I think for this problem, delta is equal to 0.25 or 0.5, excuse me. Okay. So let's go ahead and do that. And so what I'm going to do is I'm going to multiply by delta. Okay. Just to get the deltas out of the denominator. Okay. But again, this simplification, so this is basically just a simplify step. Okay. This is just my own personal preference. And so if you prefer to keep the deltas in the denominator, that is fine too. As long as you are consistent. Okay. So remember, just that's the important thing. Just kind of stay consistent with your math. Okay. Okay. And so if I simplify this a little bit, I multiply by delta squared, we get 2. Okay. I'm going to combine together the diffusion terms. And so remember, for the diffusion terms, we have 2 like terms. Okay. So you have a minus 2 phi I comma j. This is phi I plus 1 comma j plus phi I minus 1 comma j plus phi j plus 1 phi j minus 1 minus 4 phi comma j. Okay. All right, and then on the right-hand side, we have our convection terms. And so we have 3 over 2 times delta, okay, times phi I plus 1 comma j minus phi I minus 1 comma j plus 80 xi times delta, okay, times phi I comma j minus phi I comma j minus 1. Okay. Plus cosine of pi y. Okay. All right. Pi y j. Okay. All right. So in the interest of time, I'm going to stop it here. Okay. But just know that this is basically where you would take it. And so from here, you would apply this equation to the interior nodes. Okay. And so the way you would do that is you would plug in the specific values of I and j for the node. Okay. All right, so that's the interior node equation. Let's go over the boundary condition nodes. Okay. I'm going to skip over the Dirichlet boundary condition because I think everyone kind of has that one down pretty well. Okay. Let's talk about the Neumann boundary conditions in 2D because that one is a little bit different. Okay. And so the Neumann boundary conditions in 2D, they take the form of what I call a normal derivative. Okay. And so let's take the one on the bottom, for instance. And so on the bottom, okay, on the bottom, we have partial phi, partial n is equal to 20. Okay. And so the reason I have it in this form is that this derivative takes place in the direction normal to the boundary. Okay. Right. And so when you see this expression on a particular boundary, you have to ask yourself, which direction is the derivative going to take place in? Okay. And so for the bottom, boundary, that direction is going to be up and down. Okay. And so, the derivative that we actually have here is actually partial phi partial y is equal to 20. Okay. Because the bottom boundary is a horizontal boundary, and so the direction normal to that horizontal boundary is going to be vertical. Okay. 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 And so let's go ahead and plug this in. Okay. And so just like we did in the 1D problem, we're going to take our derivative here and replace it with a finite difference. Okay. Okay. And so for a Neumann boundary condition in 2D, usually the form that we like to use is this one here. We take we take the node that's on the interior, so phi interior minus phi boundary, and then we divide it by delta, and that's equal to the 1. Okay. Okay. And so I've seen a lot of confusion on this, and so let me go ahead and demonstrate with kind of a concrete example. Okay. Okay, so I've recreated just the bottom boundary of the domain. Okay, so we have nodes 1, 2, 3, 4 that's on the boundary, and then we have 5, 6, 7, 8, which are the nodes that are just immediately above it. Okay. Okay, and then we have partial phi partial n is equal to 20 on the bottom. Okay. All right, and so of course we're going to be applying this to all of the boundary nodes on the bottom. Okay. And so for instance, let's do it on node 2. Okay. And so for node 2 is the node that's actually sitting on the boundary. And so we have phi boundary is equal to phi 2. Okay. Right. And then if we're going to plug in for this equation exactly here, we also need the identity of phi inner. Okay. Okay. And so for phi inner, we're basically going to go in the direction that's perpendicular to the boundary, and we're going to list out the ID number of the first node that we see. Okay, all right. And so here we have node 2, so I've circled it in purple for you. Okay, we know that we're going to take the derivative in this direction, in the upward direction. Okay, and so for phi inner is going to be the first node that we encounter going in that direction, which is phi 6. Okay. All right, so let's go ahead and plug these into the equation. And so our equation here is phi inner minus phi boundary divided by delta is equal to 20. Okay. And so in this case, phi inner is phi 6, phi boundary is phi 2. Okay. Divided by delta is equal to 20. Okay. We can go ahead and move that delta to the other side. And so we get phi 6 minus phi 2 is equal to 20 delta. Okay, and that would be the boundary condition equation for that boundary node. Okay, so this is for node 2. Okay. Okay, all right, and so that's about it. So that's about all I had time for this review. Okay, so hopefully it was useful. So of course, I focused this review mostly on just kind of this procedure of applying finite difference to the equations, because that was kind of the weakness that I saw in a lot of the homeworks so far. I didn't really go over a lot of conceptual information, and so for the conceptual information, definitely check out the study guide, read the conceptual learning objectives, and see if you can answer them. Okay, so that'll help a lot. But for this review, I wanted to focus on just the procedure of how to take a differential equation, apply finite differences to it, and then obtain an algebraic system of equations. Okay, because that's basically what I'm expecting you to do on the exam. And so the two examples that we went through today, I know the second example was a little bit abbreviated because of the time. That's basically what I'm going to expect from you on the exam. Okay, they're not going to be these problems. Okay, so I'm not going to copy these problems onto the exam, but you should know how to do basically the process that we outlined. Okay, and just like I mentioned before, it's I don't want you guys to just kind of plug in plug into the interior node equations and things like that, because I know we have equations for that in the notes, but I want you guys to demonstrate this process for me. Okay, so that's what's more important to me for this exam, is that you can follow that process and apply finite differences. Okay, all right, so I'll go ahead and stop the recording here. And so hopefully this was useful to you. If you have any more questions before the exam, you can always send me an email or come to office hours. But if not, let's go ahead and stop this.